Okay, so for the homework, yeah, I guess question one was, so we had this notion of a Bayes optimal policy for a given prior over the hypotheses. And then question one was asking to show that that if you had a prior psi over the hypothesis class, and then we assume this prior was, or we assume the hypothesis class was countable and the prior was had full support, so all of every hypothesis had at least some non-zero probability. And then given this, yeah, we defined a good notation. We defined pi t star of some, I guess maybe we defined pi t of like ut, where this ut was the t time horizon utility associated to some reward. So we have this family of Bayes optimal policies, and then the question was to show that if the hypothesis class is learnable, then under these conditions, this family of Bayes optimal policies is a learning family, or a family of learning algorithms. So I was going to ask Adi, would you be open to walking us through your solution?
Sure. Let me open my own solution. One moment.
Hey, thank you for being willing to do that. Thank you.
Sure. Okay, so we wanted to prove that it's a learning families. We need to check the condition. So we need to take to show that the regret is bounded. So let's can you write the expression for the regret? It's like u star t. I'll do a split screen sort of thing. One moment. Is it possible to split? Yeah, I think so. Okay. We want the regret to go to 0. Which is u star t of eta minus the expected value of eta on pi t ut. Now I'll also like to write down what's the meaning of the fact that these are Bayes optimal policies. So it means that for any other stochastic policy pi prime, we have that if I take the average over an environment according to H of the expected utility of pi star t. Am I missing a star? I'm probably missing a star earlier. Okay. Is greater or equal of the utility at time t is greater than or equal to the same expression with pi prime.
Mm-hmm. Right. So this is the defining characteristic of the base optimal policy for this prior that the expected value of the expected utility is is optimal.
Now, I'd like to apply the dominated convergence theorem, which states that, well, I looked it up for the homework, but if I remember correct, it means that if the functions are bounded, then their convergence to 0 is equivalent to the convergence of the expected values. So the earlier condition, I want to switch what I need to prove, the fact that the regret goes to 0 with the fact that the average regret goes to 0.
Mm. Okay, so we know that the regret for, I imagine we take pi prime to be the a learning algorithm.
Mhm.
And we know that this goes to 0. So, and then we can apply the dominated convergence theorem to say that then the expected regret when sampling from the prior also goes to 0.
Mhm. Okay. Yeah. So pi. Yeah. That's from the fact that pi prime learns h. Sure. Yeah. Here it's 9 at night. It's little late. Okay. So now, since h is countable, this means that there is a positive probability to any environment. And suppose that I want to prove the result by contradiction. So let's suppose that pi prime, pi star t doesn't learn h. Then it means that the regret should not tend to 0. This means that like there is at least one environment which for which this limit is not 0. The regret does not go to 0, which means that there are infinitely many places in which infinitely many times in which the regret is bounded away from 0 along this environment in these times.
So okay, if I'm following, we're doing an assume that based on optimal things don't learn.
Mm-hmm.
So that means there exists an environment eta for which the regrets pi star t of eta does not converge to 0.
Mm-hmm. Which means that there's a subsequence of t's such that the regret is larger than some constant c, which is larger than 0. Mm-hmm.
Yeah, so maybe it's worth mentioning here that I think some people just kind of did a bit of a jump here and said that, okay, if it doesn't converge to 0, that means it stays banded away from 0. But that's not exactly true. Like the right thing to say is, as Ati said, is that there's a subsequence of times where it stays banded away.
Mhm.
Okay, and then
And then that means that if I now take the average regret, then it should be like at least the probability of this environment times epsilon.
minus Ti. Right. Which is again a positive constant. And I guess this this is enough to contradict the previous result that it
This is based,
I guess that's one thing we should say, maybe, that if we call this 1 and then we had this 2 counting backwards, then I guess yeah, 1 and 2 together implies that expected regret of the base optimal policy goes to 0. And then, yeah, this is now a contradiction with the let's call this 3.
Sorry, why do 1 and 2 imply the expected value tends to 0?
Yeah,
Because
so let's see.
we bound
Yeah.
it below by the
Well, we banned the expected utility below, but in the regret, it's the regret is with a negative sign, right? Because
oh yeah,
it's the
right.
optimal one minus that, so it ends up being it bans the regret from above.
Yep.
So
Yep.
if
Yep,
the upper bound goes to 0, then the the base optimal one should also go to 0. All right. Yeah, I think that works. Did it make sense to people? Any questions?
So, am I right that this proof really relies on the reward being between 0 and 1, or the reward is bounded?
Yeah, I do think it relies on the reward being bounded. Yeah.
And does the statement rely on the reward being bounded as well? Or is the statement always true?
I suspect the statement also depends on that. I could imagine a hypothesis class and the prior where there's some very low probability environments according to the prior that have like really high reward, and it kind of cancels out. Yeah, it could be interesting to try to write down a counterexample. But yeah, I would expect that that sort of thing that can happen, and it would cause problems. Right. Yeah, any other questions about this? Okay, so yeah, this was a kind of reasonably straightforward proof using the definitions. I guess it, as you pointed out, it needed some of the assumptions, like you applied the dominated convergence theorem. We needed the rewards and the regret to be bounded. And yeah, I guess it shows that the Bayes optimal policies are quite powerful, but I guess they're only powerful if we have a good prior, in the sense that the prior is not dogmatic; it doesn't exclude any of the hypotheses. So that's an important part of it. I guess I didn't write it here, but it is important that I assume that the support of the prior is all of H. So that was an important condition. Okay, so maybe.
Thank you so much for going through that, Adi. Thank you.
Yeah, thank you, Adi.
Thank you.
I have one question. How did you know to analyze this quantity, the expected regret? How did you figure that out?
Well, it's like that's the tool, that's the only tool I can apply to get something which looks like what Bayes optimality. If I want to contradict Bayes optimality, I think applying expected value to which looks like almost the expected value of the regrets.
Thank you. Thanks.
Yeah, I think the general principle is use every condition in the statement. And if you haven't used it yet, then you probably need to use it somewhere.
Maybe in the future I'll add additional conditions just to trick you.
Oh, but that'll be me.
That would be very new. Well, but I guess it's a little bit closer to real life, because in real life you don't exactly know what conditions you need. So sometimes you like assume some things, you realize you need something else, you realize you didn't actually need something that you were assuming. But yeah, on a homework it would be hard. Okay, so maybe we can move on to question 2. So in question 2, we're asking, okay, let's assume we have a, actually question 1 and question 2 had like some relationship, because the Bayes optimal policy can actually always be chosen to be deterministic. That kind of suggests that maybe things are always learnable by deterministic policies. And that's actually like not wrong in kind of spirit, like as you'll see, or I guess as you already saw when we talked about the bandits, the exploit and commit was a fully deterministic policy, and that's often the case that we can, for sort of hypothesis classes that appear naturally, we can construct a deterministic learning algorithm. And then this question was kind of looking into it, whether that's always the case. And maybe Matthias Meyer, if you're available, could you walk us through a solution?
Yes. Yeah, so the idea, so we construct a counterexample, and the idea is that we want to have adversarial class of environment. So for each deterministic policy, we want to build an environment that's like exactly acts against this specific deterministic environment policy. So it's enough to choose the observations and actions to be the binary set 0, 1. And we basically play the game that the agent is supposed to predict the environment. So the agent moves first. And the reward is always 1 if the agent correctly predicted the environment in the last time step. So the reward only depends, like the reward for
history is AT equals OT. So it's basically you're trying to get the agent to guess what the next observation is going to be and get a reward if it's correct and 0 if not.
Right, and now we construct, so we take now a deterministic policy. And we want to construct an adversarial environment. Right, so how we do that is whenever the policy predicts a specific observation, then we just choose the opposite. But we only do this if the trajectory already was how the policy should be.
Okay, so if the policy on a certain history returns action A, then we let the environment after that action return the opposite of the action. And then there was a condition that...
Yeah, and I think it's important that we do this if the history up until t-1 is actually...
It's compatible with the policy.
Yes, and otherwise we just take uniform distribution over the observations.
And maybe let me write out for people what compatible means. So if you have a history like this, AT, OT, then because the history is compatible with the policy, if whatever happened so far is what the policy would have done. So if if I equals pi of h up to maybe I minus 1. So I guess concretely this means that A0 is going to be pi of the empty string, and then A1 is going to be pi of the A0, 0, and so on. So basically hopefully this makes sense to people. And then you said if they're not compatible with pi, then we take eta pi to be random or uniform between the two.
The uniform distribution.
So with probability 1/2 it returns 0, with probability 1/2 it returns 1.
Yeah, now our environment class is just all these adversarial environments. And now, given any deterministic policy, yeah. So now, because it's adversarial, we should have like utility 0 or something. Yeah, because in each step we just take the opposite of the environment of the policy, and this should be like continually compatible, I think. Then we have utility 0 in all steps. And if we just, and then we have to argue, okay, now what could we, like, what's the optimal utility you can get for this environment? And because as soon as you choose something which the environment didn't adversarially predict, so you are better than the deterministic policy, the environment flips to random. So the best thing you can do is have utility 1/2.
Right. So basically, the optimal policy against this environment is something that does the opposite as pi in the very beginning, and from then on, already the environment is in the phase where it's uniform.
Yeah, and then it doesn't matter. You can do anything.
It doesn't matter what the policy does. We always get utility 1/2. Yeah, it's believable. So here we get that the regret for all t is I guess 1/2. So it doesn't converge to 0.
Yes. Yeah. So any deterministic policy has there's an adversarial environment where you have regret 1/2, and now we have to construct a policy that actually learns this class of environments. And for this, we just take the policy which always puts out a random observation, so it just predicts the uniform distribution, or like it's uniformly at random chooses an action, which is the prediction for the observation.
So it's uniform. Which is okay. I guess we took the actions to also be indexed by the same thing. So this is like 1/2 times action 0 plus 1/2 times action 1 in the as a distribution over actions.
I guess writing 0 is not a good choice.
Yeah, maybe it's like in quotes. Hopefully people understand.
Yeah, so right, and this now learns all these environments, and by doing this, let's take any environment in the class, and this means by construction there's a policy that's deterministic where this environment is an adversarial environment of.
Sorry, say that again. We pick an environment.
Yeah, no, there exists a deterministic policy such that eta is the adversarial environment to this policy. And now, since pi or pi tilde chooses random observations as its actions, by like standard probability calculus, you get that there will be, with probability 1, a time point at which you choose a different action than pi. Because always choosing the same action is like probability 1/2 times 1/2 times 1/2, which is 0 in
Yeah,
the
so
limit.
maybe we can try to be a bit more precise. So the probability that pi tilde of h equals pi of h for all like histories up to time t. I guess it should be
Like a
bounded above by
particular evolution,
minus t.
not, yeah. It's not
Yeah.
all possible histories.
It's not.
Just the ones.
Okay, so yeah, what do we mean here? It's like given a history h in the probability that the kind of truncated versions, the actions at each time point are the same for t less 3/4 t.
Yeah.
So for each time t, there's probability 1/2, and these are independent. So this is bounded over by 2 to the minus t.
Yeah, and so that means that the probability that in the whole destiny we choose the same action at every step is probability 0.
Mhm.
So there will be a time step with probability 1 where you choose a different action, and from this point on, the environment reacts randomly again. And since we then have a random policy which interacts with a random environment and they're both uniformly distributed, you get utility 1/2 from this point on. And because in the limit, then the finite beginning of the destiny doesn't matter. That's, yeah.
Yeah, I think it's a good high-level argument, but I guess ultimately we care about the kind of the expected value here, right? So maybe we can try to work out just more explicitly what the expected value of under pi tilde and eta of ut is. Right, so I guess we can use this to say that yeah, how does this work?
Some kind of geometric series.
Yeah, so I guess we get something like if the policy deviated in the very first step, then we get reward like 1/2 times t times 1/2, and then plus we get like 1/2 t times or 1/2 t minus 1 if the first step was right, but the second step was wrong. We get like this one. And so on. We get this sort of sum. And then finally we get 1/2 times 0 times 1 over 2 to the t. Does that seem right? At least in spirit.
Seems plausible, but I haven't actually calculated this.
Yeah, there might be an
Yeah.
off by 1 error, but I'm pretty sure. Yeah, that's good.
Yeah, it could be off by 1, but okay, let's assume this is like more or less right, and then I guess the idea is we can probably sum up this series. And what do we get? Or I guess, so for average regret, there should be like a 1 over t in front of the whole thing. So yeah, ideally, you would get that it's 1/2.
Yeah, I think you look at the order constant term and you ignore all the order 1 over t terms, maybe.
Yeah,
You get a quarter plus an eighth plus a 16th.
right. So
Oh.
we can we get like 1/2 times and then the t over t cancels, and then we get 1/2 plus 1/4 plus and so on. I guess up to 1 over 2 to the t or minus 1. And then plus we get the, or I guess minus we get some like order of 1 over t terms, which is maybe like 1/2 over t times 1/4 plus 1/8. Okay, so yeah, and then this thing is bounded by 1/2. So yeah, I think in the limit we get that this converges to 1/2 in as t goes to infinity, which is the optimal the optimal average reward. So this is indeed this is indeed a learning algorithm.
Is this in some sense the simplest possible counterexample?
I think all counterexamples are like pretty like similar in spirit, at least. Like you basically, I think almost all of pretty much everyone's solutions did this sort of idea where you take a deterministic policy and then you construct an environment which is adversarial, or in which that policy performs badly. I think you could maybe like simplify it a little bit, but it's also kind of up to taste of like what counts as simple. So I think this is close to being one of the simplest ones.
Maybe a small simplification would be to say that once the policy is lucky or the agent is lucky, then you just get one reward all the time.
Right. Yeah, I think that's that instead of taking the policy to be uniform whenever the policy diverges from this fixed pi, instead we could just take the reward to be constant 1 there. So that, I agree that would probably simplify things a little bit. So maybe that's one simplification. I think when I was thinking about it, I was thinking of, instead of like the policy trying to predict the last observation, I was just taking the observation to be the reward itself, and then the observation would stay 0 as long as the policy is doing a certain deterministic thing. So that's, I don't know if that's simpler, but that's just another way of approaching it. So yeah, I think on the high level, the kind of the idea remains the same, and you can do different variations on it.
Do you need h to be infinite?
Do we need H to be infinite? Yes, I think.
I think so, because we have infinite trajectories, and therefore we have infinite number of policies.
You even need
Sorry.
H. Yeah, sorry.
I meant that not infinite trajectories, but like unbounded length, and we can have like, therefore we have a countable infinity of policies.
But then I think that policies, there are uncountably many policies. Right?
Yes. So
Yeah.
if you have a restriction to H, to big H, so the set of policy being of environment being countable, then you can prove the opposite, that you can build a deterministic policy, I think.
Yes, I think that's true as well. I guess we sort of.
Via some kind of diagonalizing argument.
Yes. So you build using, at least that's what I thought, that you could build a kind of diagonalization by kind of derandomizing, and for larger T, you derandomize for larger and larger number of policies, which are always finite. And then you can have something that has regret going to 0 for countable numbers, a countable number of environments.
Yes, yeah. So I think, yeah, I think that's right. I think for countable hypothesis classes, you can indeed always have a learning algorithm which is deterministic. And I guess we came sort of close to this in question 1 actually, because I guess in that setting we didn't look at anytime learning. We looked at a family of Bayes optimal policies, but as you mentioned, the Bayes optimal policies can be chosen to be deterministic. So, and they're the assumption that the hypothesis class is countable was indeed also crucial. So yeah, there is we can see that there is a kind of qualitative difference between countable and uncountable here. Yeah, and then maybe one thing that's worth mentioning is that we kind of had to work a little hard to construct this hypothesis class. Like we specifically like built the hypothesis class to beat every deterministic policy. So I think that's sort of a common phenomenon that, for example, you can ask a similar question of like, is any hypothesis class which is learnable, is it going to be always anytime learnable? And that's also false. But it's a similar thing where if you wanted to construct a counterexample, you'd have to work a little bit hard and be like specifically focused on constructing something for the sake of the counterexample. So like yeah, maybe this is not a precise statement, but like if you took like if you came across a hypothesis class which was learnable, it would be a safe bet to guess that it's anytime learnable and learnable by a deterministic policy. But yeah, it's interesting to see this counterexamples too.
So is there some kind of like a nice compact description of hypothesis classes that are such that if that hypothesis class is learnable, then it is also anytime learnable and stuff like that?
I'm not in for generality, no. I think it's like, yeah, you can show that if, yeah, as Jean-Marie mentioned, you can show that, for example, for deterministic policies, you can show that if the class is countable, then it's always learnable by a deterministic policy. It's probably not quite. Actually, I don't quite remember a good counterexample for anytime learnability, but I would think that might not even require countability, but I'm not sure. But yeah, I don't think there's
I think you can probably do it with a single policy, with a single environment. You do something like, tell me how many reward you want, and I give you exactly this number of reward, and that's what the environment does. And then you need a way of telling the number of reward which does not take too much time. So, for example, you say 0 and then you say 1, and the number of 0 before the 1 gives you the total number, gives you you exponentiate it and it gives you the total reward you get. And this will be this will not be anytime learnable, because you must say that the rewards start at some point.
Yeah, that's a good example. Yeah, I like it. Yeah. So yeah, for there you can construct a counterexample with a single environment. Yeah, I like this example. You basically at the beginning tell the environment how much reward you want, and if you wanted an anytime learning algorithm, you're not allowed to say infinite reward, but that's the kind of optimal one. So any single policy can only claim a finite amount of reward, but there's a family of policies which like claim higher and higher reward. So yeah, that's a very clever example. Yeah, I guess going back to Mateusz's question. Yeah, I don't think there's any kind of theorem that says like these are exactly the kind of hypothesis classes that are learned by a deterministic policy or something like that.
Is it intuitive why we can find a Bayes optimal policy that's deterministic, or is that some complex theorem?
I think you can have an intuition for it. It's basically, so we took Bayes optimal policy. What was the addition? So this is something in argmax of the expected utility when we sample the environment from the prior. And then, so let's see, we're looking at the space of stochastic environments, which is it's a compact convex space, and on this expected utility is a convex linear function, which is stuff that we looked at in the first homework. And I think it's always true that like an affine function on a convex set will attain its maximum somewhere for one of the extremal points, which is one of the corners of this. I guess for infinite time, this would be a kind of infinite polytope, but I think it's still true that it will have to attain its maximum at one of the vertices, which are the deterministic policies. Right? If you imagine like a polytope, and then let's say like utility increases in this way, then there's always gonna be some vertex at which it's maximized, and those are the vertices correspond to the deterministic ones here.
What are the conditions on U again for that to be true?
Let's see. I guess I mean, for this argmax to be attained at all, we want to suppose that U is continuous in the destinies. But the fact that it's affine linear, I guess, is just because we're taking the expectation here, and that one is a linear operator. So I think, yeah, you being continuous in the destinies, I think is sufficient.
In what sense is this affine? As a function from environments to expected values of utilities?
Yeah, what I mean is like you can consider this function as a function of, let's call this just I guess u pi as a function from stochastic policies to 0, 1. And yeah, it's an affine linear function like this. Like if you mix policies, you get the corresponding mixture of utility, I think.
So this is not assuming actually anything about the reward at all.
Not a, yeah. If you take this utility to come from a reward like u gamma or ut, those are automatically, the way we define them, if the reward was bounded, those are automatically continuous. So in that way, yeah, we don't. I guess we're assuming the reward is bounded. I think maybe that's the only thing.
Sorry, the vertices of this polytopia are like vertices in the space of policies, roughly, something like
No, exactly. It's a. I guess we did this for the kind of dual of looking at the environments, but on the first homework we saw that there's like spaces of policies or spaces of stochastic policies or stochastic environments. They're basically polytopes, and the vertices are exactly the deterministic one.
all becomes clear. Yeah, I didn't really realize the significance of that in question 1 of week 1, but now I see why that's significant. Did we work out whether it is or is not possible to do this same counterexample that we did in question 2 with a countable hypothesis class? The one that we discussed is not countable, right? Is that...
It's not countable. It's yeah, it's uncountable. And then, yeah, as Jean-Marie pointed out, for a countable hypothesis class, we can prove that it is always learnable by a deterministic policy. So, in fact, yeah, that is a crucial property of this hypothesis class, that it is uncountable.
So a fun question, maybe not very useful, but can we do uncountable but smaller than the one we used?
Right, like something that's not continuum.
Yes.
Yeah, right.
But like means smaller than continuum.
I guess assuming the continuum hypothesis, the answer is no.
Yeah.
Yes, of course. Or it's not about continuity, it's that it's smaller than the cardinality of the reals.
Yeah, I think the question was unrelated to this proposal. I think I was just asking. So if the utility function was defined on, I just answered this question separately, on as a function like this, which maps these infinite destinies to 0, 1, and this is a so this is a topological space, which it's the infinite product of I guess the product over omega of A plus O. So it has a product topology. Yeah, so yeah, maybe it's actually, okay, so we're at time, so if people need to go, feel free to go. But I think this is probably a good discussion point that Cooking Glass asked of what would a non-continuous utility function look like? So I think one example could be that, let's say there's only one action and there are 2 observations, for example. Then you can define a utility function. So in this case, it's just from the counter set 0, 1, 2 omega to 0, 1, which maps d to 0 if d sub t is equal to 0 for all t, and 1 otherwise. So this is an example of something. You can check this is actually not continuous. The reason being that no matter how far in the sequence a 1 pops up, it like immediately changes the utility to 1. But as we said, like u sub t or u sub gamma, the ones we defined as like the sum of these discounted rewards for average of these discounted rewards. These are continuous because what happens kind of far down a long time, kind of the influence of that decreases over time. So yeah, hopefully that clarifies continuity a little bit.
Oh, it's also clarified another notational question I had, which is that D, you're using D to refer to destinies, which refers to infinite sequences, whereas H is used for histories, which refers to finite sequences.
Yeah, yeah. Sorry, I guess I didn't clarify that terminology, but yeah, destiny means like until the end of time, and then history means like up to now, which is I mean. Okay, so Gurkinglass has a question in the chat, which is the single environment learnable anytime, learnable distinguishing example, and discontinuous in utility? Well, that example, I think you can define in terms of rewards, and you can talk about the learning in terms of like this u sub t. So you don't run into issues of utility, but it is true that like, so these, and that's actually probably a good reason why we introduced this in the first place. And I think you asked about like, can we take the limits at the beginning? So if you can take the limits if it exists, and you can always take the lim, for example. You can take the lim of ut as time goes to infinity, but this in general will be not, in general is not continuous anymore. So it's a limit of continuous functions, but the limit itself is not continuous, which happens often. Did that clarify your question?
Why do we care about like learning that's not anytime? I feel like anytime has a like intuitive explanation that there is like one agent which has this policy and learns which environment out of the class it is in and responds accordingly in the best way. I'm not sure what it means to change your policy per time step, but it's not actually a policy that the agent can execute.
Yeah, that's a good question, and I think it's true that arguably anytime learning in some ways is like, well, I don't know. I guess in principle it can happen that you know how long you're gonna play a certain game or interact with a certain environment. So having a family of learning algorithms is reasonable in the sense that, okay, you're told how long you're going to play, you choose your learning algorithm accordingly, and you don't need something that works for all of those regardless of time. It can just work for the given the time that you were told. So the question is whether you're like told how long you're going to be playing or not. And so if you put it that way, maybe it's reasonable. And I guess maybe a sort of practical reason is just that often non-anytime learning is a little simpler technically. Like as we saw in explore then commit, it's helpful to be like, okay, we know how long we'll be playing this bandit game. So given that this is how long I need to explore, and then you can turn that into an anytime learning algorithm, but the resulting algorithm is more complicated technically speaking. So it's often just helpful sort of pedagogically or in terms of developing understanding to start with a non-anytime where you know the time horizon, and then if you want, you can try to generalize to any time where you don't know that time horizon.
But when you have this dependence, it only works in the limit, right? Like the t needs to be very large.
Right. Yeah. That's true. Yeah. So yeah, the kind of non-anytime is somewhat limited, where it's assumes you know the time horizon, but still the learnability only says something about the long-term average. But I mean, if you have a explicit regret bound, like we had for export and commit, even though the limit is only at this time equals to infinity, the bound is meaningful for a finite time. You can say like, okay, if I play this for 10,000 time steps, then my regret is going to be like less than 1% or something. So in that sense, it's still a meaningful thing to study. As I said at the very beginning, the sort of considering the limit going to 0 is sort of the weakest condition we can discuss for a notion of learning. But in practice, we often want something stronger, which is an explicit regret bound that says like, okay, if you play for this long, this is how much regret you're expected to accumulate on average.
Maybe you can have even weaker things, like maybe you learn every environments except finitely many ones.
Yeah, you could do that, but well, I mean, what if you end up in one of those finitely many? And then it's sort of, yeah, I guess it's a weaker condition, but it sort of feels a little too weak at that point where, because also your hypothesis class might be finite. So let's say you have 10,000 hypotheses, and if your condition is you learn all but finitely many, then you don't even need to learn any of them. And so maybe in that sense it's a little too weak. But yeah, I could imagine maybe scenarios where that's interesting to consider too.
I mean, maybe if it's actually not learnable, but it's learnable except for a small class of environments, then you still want to find that algorithm.
Right. But in that case, if something like that happened in practice, I think what one might want to do is to actually narrow down the hypothesis class, like identify the thing that makes it unlearnable and narrow the class down to something that's learnable. And then that way you kind of have two results. You can show that the bigger class is not learnable. Let's say you have a counterexample for it. And then you have just the kind of still reasonably large but smaller hypothesis class, which is learnable. I think that would be one way to proceed in that scenario to understand it. All right, thanks, Christian. Yeah, I guess we're like 10 minutes over, so maybe we can stop here and wrap up for today. Yeah, thank you, everyone, for the. Thank you especially to Adi and Matthias for presenting their solutions, and thanks everyone for questions.
Thank you. Thank you.
Bye-bye.
Bye.
But
Bye.